Today on the Perception in Action News, can skill execution be improved by combining self and expert models with video feedback? How are affordances used for striking and defending in combat sports? And a look at a new study of mine on team coordination in baseball. So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. In these news segments, my goal is to dig through that ever-growing pile of article PDFs so you don't have to. Before I dive into today's articles, I wanted to mention a couple of other things. First, thanks to Edward Coolin for forwarding me a really cool YouTube video by Smarter Every Day. Link in the show notes. This video is about the challenge of learning to ride a backwards bicycle. That is, a bike that has been engineered to have reverse steering controls. So you turn the handlebars to the left and the bike goes to the right and vice versa. The gist of the video is that it's nearly impossible to ride this bike right away. And after hours and hours of practice, you can eventually do it. But then, if you try to switch back and go to riding a normal bike, you are messed up for a while. I found this really interesting because it's essentially a more extreme version of something I've played with around a lot myself, prism adaptation. I posted a vlog about this a few weeks ago in case you're interested. Again, link in the show notes. Basically, with both the bike and the prisms, you have to go through a major perceptual motor recalibration, which I discussed back in episode 53. In the case of riding a bike and throwing, which is the task I use with prisms, this is extremely difficult because it requires you to break into a very well-learned, highly proceduralized skill and essentially reprogram it. And once you do this, you get a negative after effect, as you essentially have to unlearn this recalibration when you go back to a regular bike or take the prisms off. But, and I bet this would happen with the bike too, if you keep switching back and forth, you can eventually switch between calibration states relatively easily. So you can do one and then the other without much of an interference. Anyways, it's a really well-produced, fun video, so definitely check it out. The other thing I wanted to mention is a recent blog post where I posted an abstract for a paper I will be writing over the summer. Yes, I do have a blog, but I don't post there very often. You can find it at perceptionaction.com. This paper is a large-scale study of transfer of training from my baseball batting simulator to real baseball, which involved over 10 years of data collection. For those that have access, this was also posted as part of a new project I started at ResearchGate called Training and Understanding Sports Skills Using Virtual Environments. So please check out those if you are interested. Links in the show notes. Now on to the news. Dateline, International Journal of Sports Medicine, February 2017. Throughout the podcast, I've been trying to convey that I'm a strong believer in the idea that there's no one perfect technique performers should be striving for. Instead, we have, as Latash wonderfully puts it, a bliss of motor abundance. That is, there are a multitude of possible techniques that we can use for any skill. And this allows us to optimize a perceptual motor strategy for our own personal set of constraints. However, the idea that there's not a perfect technique should not be interpreted as meaning there are no bad techniques. A bad technique, in my mind, is not one that does not conform to some traditional ideal. Instead, it is one that involves movements that are highly likely to lead to injuries if they are continued. For example, not having correct knee bend and placement on landing. In this case, I think a coach or trainer should be definitely stepping in and correcting the technical flaw in some way. But again, we need to be careful with this too. Some movements we think might lead to injury will not do so for everyone. A good example of this is in running, where we spent several years trying to convince people that forefoot striking is bad, and we developed tools, such as minimalist running shoes, to change this. Now, I think it's more generally accepted that most people's existing running technique is well adapted for them, whatever type of strike it involves. But anyways, assuming we have identified a valid technical flaw with an athlete, what is the best way to fix it? Traditionally, this has involved very internally focused instructions, such as keep your knee over your heel. Hopefully by now in the podcast, I've convinced you that promoting this type of internal focus is generally a bad idea in the long run. For example, back in episode 13, I talked about my research on recovering from knee and elbow surgeries and showed that an internal focus on vulnerable body parts delays the return to peak performance. So there must be a better way. In the recent study, Dalinga and colleagues used video feedback as an alternative to internally focused instructions. As I think most people know, there are two types of videos that are most commonly used for observational learning. Ones in which an expert is modeling the quote-unquote ideal movement, and ones in which a performer watches themselves with the goal of learning to correct errors, what is commonly called self-modeling. In this study, the authors sought to create feedback that combined both of these. To achieve this, they developed a novel application called the Visualization of Motion Feedback Tool, or VSMO. VSMO synchronizes two videos, one of an expert performing the movement and one of the athlete being trained performing the movement. This is used to create a display which shows the contours of the two bodies overlapped and calculates a percentage overlap score, which is a nice quantitative way of assessing how close the two movement patterns are. I've included a figure showing this display in the show notes. To test the effectiveness of this tool, they had team sports athletes from sports including basketball, handball, and soccer perform a vertical drop jump. A group of roughly 30 athletes trained using the VSMO feedback, while a 30-athlete control group trained without receiving any feedback. Performance was measured pre- and post-training, and the dependent variables included percentage overlap with the expert model and a variety of biomechanical measures, including joint angles and ground reaction forces. What was found? First off, perhaps not surprisingly because they received direct feedback about it, the VSMO group significantly increased their percentage overlap during training, from about 82 to 85%, while the control group stayed roughly the same, at about 81%. In terms of biomechanics, there was a really interesting gender difference. For male participants in the VSMO group, the change in percentage overlap was associated with significant changes in biomechanics, including larger range of motion and smaller ground reaction forces. But for females in the VSMO group, even though percentage overlap increased, there were no significant changes in biomechanics. And of course, there were no significant changes in biomechanics for the control group. Okay, a couple points here. I think it's a good start, but in the future I'd like to see a more interesting comparison group used. For example, I think it'd be really interesting to compare the VSMO group to a traditional self-modeling or only expert modeling group. The other thing that was not clear to me is how you can get a significant increase in the percentage overlap without associated changes in biomechanics, as was found for the female participants in the study. This suggests to me that more work is needed to understand what this percentage overlap score actually relates to. But anyways, I think VSMO is a really clever idea, and I hope to see more work using it in the future. Dateline, Journal of Ecological Psychology, March 2017. One of the most fundamental things athletes in many sports must learn to control is the separation between themselves and their teammates and opponents, also called interpersonal distance. In a few moments, I'm going to tell you about a study of mine where we looked at teammates, which of course need to be able to adjust interpersonal distance in a coordinated manner so that they're all on the same page. For one-on-one opponent tasks, like in most competitive martial arts and boxing, you don't want interpersonal difference to be perfectly coordinated, but instead control it in a manner that creates opportunities for attacking and puts you in position to defend. How do martial arts athletes achieve this? This question was recently explored in a study by Okamura and colleagues in the sport of Kendo. For those that don't know, which included me before reading this paper, Kendo is a Japanese martial art that involves fighting with bamboo swords. To be successful in this sport, the players need to continually vary their interpersonal distance to create their own striking opportunities and avoid those of their opponent. This presumably relies on their ability to detect the affordances for each of these. To investigate this skill, Okamura and colleagues used a two-step approach that is common in ecological psychology. First, they measured the perception of the affordances for striking and defending. Then, they looked at how actions made during a match relate to this. For this study, 6 experts, who had previously competed for Japan, and 6 intermediates, who had no formal competition experience, participated. For the perception task, players faced an opponent, then moved towards them until they reached the furthest distance at which they felt they could strike successfully. They then started close to the opponent and moved back until they reached the same distance. The average of these two was then taken as the measure. The same procedure was used to find the separation which afforded defending. For the action part of the study, video recordings of real matches were used to analyze stepping behaviors. What was found? In terms of the perception of the affordances, both the experts and intermediates had a bimodal distribution, with an area relatively close to their opponent for striking and an area further away for defense. In terms of action, the experts did a better job of staying in one or other of these zones and spent less time in the messy middle, which is not optimal for either. The stepping behaviors during the match also seem to be tightly linked to these zones. For example, at the far interpersonal distance, experts tended to step forward to their opponents to enable their own offense. In other words, their perception and actions were tightly attuned with each other. I think this is a really interesting study that shows how affordances provide a link between perception and action. The only thing that was missing for me is a more detailed analysis of the information used to perceive these affordances. Was it truly purely based on perceived distance? I would think it'd be more complex than that. For example, the posture of one's opponent and position of their stick need to also be taken into account. Dateline, Frontiers in Psychology, May 2017. As I mentioned, the last paper I want to talk about is the study I recently published in collaboration with colleagues here at ASU on team coordination. This is part of a Frontiers research topic called Understanding the Successful Coordination of Team Behavior. This is exciting for me because it's my first real dive into studying teamwork after years of doing research on individual performance. A key element of being a successful team is having coordinated decision-making, or as players often refer to it, being on the same page. For a lob pass in soccer to be successful, the striker needs to break for goal at the same time. For many plays in football to work, the quarterback and receiver need to read the defense in the same way. How can we evaluate and train this type of coordinated decision-making? To date, this has really been done in 2 different ways. On the one hand, we have knowledge elicitation methods, like interviews, which pool and aggregate the passive responses of individual teammates taken out of context to assess shared mental models. For example, you could have 2 teammates looking at a drawing of a play and see if they both say they would do the same thing. On the other hand, we have studies from the ecological dynamics camp, which involve techniques which analyze the macro-level behavior of teammates during actual gameplay. For example, the movements of players from GPS data. But these studies do little to elucidate the underlying perceptual cognitive processes. Is there a method that we could use that falls somewhere in between these 2 extremes? Well, when I first started thinking about it, I thought a good place to start would be to try to scale up one of the methods we know is effective for studying decision-making at an individual level. And that's exactly what we did in this paper. In particular, we developed and tested a joint temporal occlusion paradigm. But before getting into the methodological details, let me tell you about the context we used to study team coordination. A good example of the importance of coordinated decision-making can be seen on a baseball infield.
And that's back up the middle, could be 2. There's a flip. How do you like that? Does not get any prettier then that double play.
When a ball is hit on the ground and there are runners on base, each of the 4 infielders must rapidly decide between 2 options: attempting to move to intercept or field the ball, or moving towards and covering one of the bases in preparation to receive a throw. For the 2 middle infielders, the shortstop and the second baseman, there is further complexity in that they must also decide which base to cover. For example, a shortstop needs to cover second base if the second baseman fields the ball, and third base if the third baseman fields it. In this situation, it is possible to assess the correctness of an individual player's decision. For example, if a player closest to the ball decides to field it, we might consider that to be a correct decision. However, successfully making an out on the play hinges more on the overall coordination of the teammates' decisions as opposed to their individual correctness. For example, if I'm the player closest to the ball, but clearly one of my other teammates has decided to field it, the outcome of the play would be better if I decided to go cover a bag. This type of decision-making in a baseball infield is a prime example of interactive team cognition, which proposes that team cognition is a dynamic, team-level activity that is inseparable from the context in which it occurs. As I mentioned, to investigate this type of behavior, we developed a joint temporal occlusion paradigm. I've talked about occlusion paradigms on the podcast several times now, in most detail way back in episode 4. But to refresh your memory, this paradigm involves having an individual view an unfolding event, for example, an opponent serving a tennis ball, either on video or live, and then occluding the event in some way, either spatially or temporally. Then, we ask the viewer to make a decision, using a response that could be either passive, for example, saying down the line or cross court, or active, for example, stepping in the anticipated direction of the ball travel. To scale this up to use as an assessment tool for teamwork, we did the following. To create the occlusion videos, we launched balls onto an empty practice-sized baseball infield at different horizontal angles. There were 8 different angles used. For example, a ball hit straight over second base, a ball hit close to the third base line, etc. We also used different speeds, but I'm saving that analysis for another paper. The balls going out onto the field were simultaneously filmed using 4 HD GoPro cameras, which were each placed at the typical starting positions of one of the 4 infielders. So we have the first baseman's view, the shortstop's view, etc. We then edited each of these videos so that only the first 250 milliseconds of the ball flight was shown. When viewing these videos, participants were given 2 response choices. Say ball if they would attempt to field the ball, or say the name of the bag they would cover if they decided they would let another player on the infield get it. But again, we didn't care so much about what an individual player decided to do. We were more interested in how it coordinated with the decisions from players viewing from other locations. So, as kind of a first validation test of this method, we wanted to see how team makeup and experience would affect performance on the task. For the experiment, 120 participants were divided into 30 groups of 4 players. Each group included 4 experienced current players, 1 first baseman, 1 second baseman, 1 shortstop, and 1 third baseman. Each of the 4 players watched videos from one of the 4 viewpoints in separate rooms, and their combined performance was analyzed as follows. First, we calculated the average decision time for the 4 of them. Second, we assigned their response to each ball trajectory a coordination score. This score was based both on the assessment of experienced coaches and on the relative position of the ball and fielder at the time the judgment was made. The scoring system was as follows. They received 3 points if the best positioned player goes for the ball and all bags were covered by the other players in the group. They received 2 points if a player other than the best positioned player in the group got the ball, but all bags were covered by the other players. They received 1 point if 2 or more players in the group indicated they would get the ball, therefore not all the bags were covered, and they received 0 points if no players in the group indicated they would get the ball. There were 3 types of groups that participated in the study. Group type 1 we called teammates. These were college baseball players from the same team who each viewed videos from the camera location corresponding to their own playing position. Group 2 we called non-teammates. These were college baseball players that were from different teams and brought together, and each of them viewed videos corresponding to their own position. And finally, group type 3 we called Scrambled Teammates. These were college baseball players from the same team, but they viewed videos from a camera position that did not correspond to their own playing position. In particular, first baseman viewed the video shot from the shortstop's perspective and vice versa, and second baseman viewed the video shot from the third baseman's perspective and vice versa. Okay, got all that? What did we find? First off, the teammates group had significantly higher agreement scores and significantly faster decision times than the other two types of groups. That's probably not all that surprising. Through experience playing together, teammates are going to know what each other is going to do in a given situation better, whether that's through a shared mental model or shared perception of affordances. What was even more interesting was that the Scrambled Teammates groups made significantly faster decisions and had significantly higher agreement scores, specifically for balls hit up the middle, than the non-teammates group. So think about that. Players making judgments from completely different positions than they normally play, that happen to be teammates, did better than non-teammates making judgments from their typical positions. We argued that this suggests that performance in this task depends on knowledge about the action capabilities of one's own teammates, for example, whether they have quick lateral movements or good range, and this is more important for team coordination than knowledge about how to play one's own position at an individual level. So this was quite a fun study, and I think the findings suggest this joint occlusion paradigm is sensitive to team makeup, and may be an effective way of studying team coordination. In the near future, we plan to extend this by filming each position from a few different viewpoints and varying that from trial to trial, and by incorporating infield shifts. Well, that's it for the news. If you're interested in more articles like the ones I talked about today, give me a follow on Twitter @ShakyWeights, where I regularly post links to interesting papers I find. And remember, you can contact me at robgray@asu.edu and find out everything you ever wanted to know about the podcast at perceptionaction.com. This is Rob Gray from ASU. Cheers for now.